Good morning, everyone. So today we will be discussing another important topic, that is the magnetic field on the axis of a circular current loop. So in the last class we have discussed about Biot-Savart's law. I told you Biot-Savart's law only gives us the magnetic field due to a current element. So how can you apply the Biot-Savart's law to get the magnetic field due to the entire current carrying conductor? So here I have taken a circular current loop and we will be finding the magnetic field at a point on its axis by using Biot-Savart's law. Obviously we have to use the method of integration because Biot-Savart's law is going to give us the magnetic field due to an element only. So how do we see? So first of all, let me take a current loop. Here the dotted line means it is on the back, solid line means it is on the front. So current loop is like this. This is the dotted line and that is the back side it is the dotted line, front side it is the solid line. So let me take the axis of the loop. So this is the axis of the loop. Okay. So suppose some amount of current is flowing. Let me take the current is flowing along this direction. Means that side current is going in and here it is coming out. So current is coming out on this side. Suppose I amount of current is flowing. As you know, in the last class I have already told you the direction of magnetic field. So since it is a current carrying loop, so what we will be doing? The loop is like this. On this side current is going in and here current is coming out. So guard your four fingers along the direction of current flow. Here you see coming out. Okay. Four fingers along the direction of current flow and the thumb will give you the direction of magnetic field. So magnetic field on this side will be this way. Okay. So we are going to find the strength of that magnetic field. Let me take a point. Suppose there is a point on its axis and we are interested to find out the magnetic field here. Suppose the distance of the point from the center of the loop is x. This is x. Okay. And let me take the radius of the loop to be r. Okay. Oh. Now, as you know, to apply the Biot-Savart's law, we have to take an element. Let me take an element at this particular point. So, suppose the length of the element is dl. So, current element will be ideal. I told you, current element is always tangential, isn't it? So, you see, the current is going in, this side current is going in, and here current is coming out. So, it will be tangential output, tangential, like this, okay, tangential. So, I am going to draw it like this. So, this is ideal current element. Okay, current element is ideal. Now, in Biot-Savart's law, we need the distance of the point from the element. So, let me take the distance. This is the element. This is the point where we are going to find out the magnetic field. So, let me take the distance to be r. This distance is r. Okay. Now, let me consider this angle to be anything, suppose phi. This angle is phi. Now, here we are going to find out the magnetic field. To find the magnetic field, first of all, what I am doing, I am drawing a perpendicular line. For what purpose you will get to know? I am just drawing a perpendicular line perpendicular to the axis. Now the question is, what is the direction of magnetic field here produced by this element? I told you, in the vector form, Biot-Savart's law, you know, dV is equal to mu by 4 pi ideal cross r. So dV means magnetic field has to be perpendicular to both ideal and r. Now you cannot draw the magnetic field here perpendicular to ideal. We don't have any idea. But at least we can draw it perpendicular to r, no? Because it has to be perpendicular to both ideal and r. Ideal cross r. That is the magnetic field. So take care that you are drawing it perpendicular to r. Now in which direction will be? Means you can draw perpendicular this way also, that way also. Along which direction the magnetic field will be? See, very easy. I told you ideal cross r. Ideal. See, ideal current is going like this. So ideal is this side. Tangential coming out. And r is this side. So ideal, you just imagine, ideal is here. Ideal cross r. So magnetic field will be like that. Okay. So at point P, magnetic field is dV and let it be this. Take care that you are drawing it perpendicular to r. Okay. So this is the magnetic field dV. Now if this angle is phi, this is also phi. How? See, this is 90 degree. So you can say this plus this is 90 degree. Again, you are saying dV has to be perpendicular to r because dV is the result of ideal cross r. So this is also 90 degree. So this plus this is 90 degree. This is common angle. So this is good. This like that you can decide. Okay. Now what is this magnetic field dV? Let me write here only now. dV is equal to, this is the magnetic field produced by this element. So Biot-Savart law says mu naught by 4 pi ideal sine theta. Hold on. What was theta? Theta is the angle between ideal and R. Okay, see, ideal is tangential like this. tangential, and R is towards on the axis. Okay, axis is here. On the axis it is coming like this. So ideal has to be perpendicular to this because it is going towards the axis, but it is tangential. Ideal is tangential. So this angle is actually 90 degree, which you cannot see from the figure. You have to imagine. Okay, ideal is tangential. Okay, perpendicular to the plane of the board, and R is going towards the center, means on the plane of the board, perpendicular to the plane and on the plane. So this angle is 90 degree actually. So it is 90 degree. Divided by distance square. What is the distance? R square. Okay. Now sin 90 degree is equal to 1, so it is going to vanish. So dB, which this magnetic field is actually mu0 by 4 pi ideal divided by R square. That is the magnetic field. Fine. Okay. So keep in mind what is R? R is root over of R square plus X square. Pythagoras theorem. That we are going to put it at last. Fine. Now this magnetic field dB is a vector quantity, can be resolved into two components. One component will be going this side. What is that? It is dB sin phi. One component is this side. It is what is that? It is dB cos phi. Now what we are going to do? We are going to take another element which is diametrically opposite to this element. So you have taken one element here, diametrically opposite take element here, means over here. Okay, let me take. So dl is the element. So with the current, what will be the direction of current element? Here the current was coming out, so the current element was tangentially out. Now here the current is going in, so current element will be tangentially inside, means just opposite to this. So opposite to this means let me draw it opposite to this, okay? So if it is ideal on this side, here ideal will be on this side. Okay? So again the distance is required, so distance is going to be this much. So if it is R, it is also R. Okay? So we are drawing it for this element. Okay. So what is going to be the magnetic field here? Same. Why? Because the magnetic field depends upon the current element and distance. Distance is same, current element is same, so the magnetic field strength will be same. Direction will be different. What is going to be the direction? See now this time. So here ideal is going in, tangentially in, and R is this side. So dl cross R. See, dl is inside. So from here you need to dl cross R. R is here. Okay, dl cross R. This time magnetic field is going down. Okay, but going down means you need to take care. I say you have to draw it perpendicular to R, but this time going down. So it will be this field. So this is also strength is same. So dB. So again, if this angle is phi, this angle is phi. If this angle is phi, this angle is phi. The logic is same as I have explained before. So this dB strength is same. You know it to write again. So this dB can be resolved into two components. One will be going this side. What is that? If this angle is phi, it is dB sin phi. And on this side it will be dB cos phi. Oh, now you see, already I told you these two magnetic field strengths are same. Now it is dB cos phi upward, it is dB cos phi downward. So these two components are equal and opposite, they will cancel each other. So what is left out? dB sin phi, both are equal but along the same direction, so they will add up. So what we got to know? So for a circular current coil, for every element of length, there will be a diametrically opposite element. If you take the element here, diametrically opposite element will be here. So for every element, there will be a diametrically opposite element who are going to cancel their vertical components of magnetic field. So for each element, the vertical component of magnetic field will be going to be cancelled by another element. So what is left out? Only the horizontal components. That means at this particular point, the magnetic field due to the entire coil is actually the summation or adding of all the horizontal components. So what we are going to do? We are going to integrate all the dB sin phi's, because only dB sin phi will be left out. dB cos phi are going to be cancelled out by the counterparts. Okay. So what we will do? Net magnetic field at this particular point. Okay, is equal to, what is this point? It is a point of the axis. It is equal to integration of dB sin phi. All dB sin phi we are going to integrate. Integration means what? Summing up. Okay, so let us put the values down. So dB is going to be this. So mu0 by 4 pi I dl divided by r square. Okay, and sin phi from the diagram. You see, take this right angle triangle. Sin phi is perpendicular by hypotenuse. Perpendicular is r. Hypotenuse is smaller. Okay, so all the constants you take it out. Mu0 is a constant. 4 pi is a constant. I, current is a constant. dl, not a constant. It is a length element you have chosen. R is a constant. Take it out. Okay. R square into R. R cube. Take it out. It is also a constant. Why? Because, see, you are taking a point on the axis. Whatever may be the element you take it here, anywhere. Ultimately, distance will be r and the same distance. All the elements are equidistant from the point, so r is a constant. Take it out. Okay. So what we are going to integrate? We are going to integrate only the all other terms are constant. So what we get? It is mu naught I r divided by 4 pi smaller cube. And integration of dl, you have just chosen a small element of length dl. If you integrate, you will get the total length of the loop. Total length of the loop means what? Circumference of the circle twice pi r. Okay. So finally we get magnetic field B is equal to mu naught is left out, I is left out, r into r, it becomes r square divided by twice pi 4 pi cut 2 is there. Okay. Now finally put the value of small r. Small r is what? It is root over of r square plus x square. So it is x square plus r square, root over means to the power half. Again cube is there, so it will become 3 by 2. So that is the magnitude of magnetic field at the axial point at a distance x from the center. Okay, due to the current loop. Now, if there are n turns in the loop, not necessary that there will be only one turn. There may be many turns. Okay, so you can write for n turns. For n turns, magnetic field will become just multiplied by n. So it will become mu naught n I r square divided by twice x square plus r square to the power 3 by 2. So that is going to be the magnetic field if there are n turns in the loop. Okay. Now there are some special cases. Number one, if the point which is on the axis is actually at the center. If you are trying to find out the magnetic field at the center, so if the point is at the center, the x becomes how much? 0. Okay, so let us put it. So at the center, x goes to 0. So magnetic field at the center will be how much? Put x equals to 0. Let us use this expression. Okay, x equals to 0. Okay, so it will become r square 3 by 2 2 cut will become r cube. So r square is there in the numerator. It will become only 1 r. So it will become mu naught I divided by twice r. So that is the expression for magnetic field due to a current loop at the center. Very, very important. Keep in mind. Okay, at the center. Okay. Now case number 2. If x equals to r, that means the distance of the point. Obviously, the point is the axial point. If the distance of the point is becoming the radius of the circle, okay, if it is so, then the magnetic field B is equal to what you put? It is mu naught I r square divided by 2 into, you see, it is also r square, so it will become 2 into r square. R square plus r square will become 2 into r square. So 2 to the power 3 by 2, 2 to the power 3 by 2, and r square, see, twice r square, 2 to the power 3 by 2 I have written. R square 3 by 2, 2 to cut will become r cube. So finally it will become B is equal to mu naught I divided by r square cut 1 r is there. So 2 to the power 1 plus 3 by 2 will become 5 by 2 into r. So that becomes the expression for magnetic field if x equals to r. Okay. And finally one more situation let us discuss. Number 3. If x is much greater than capital R, that means the point is far away from the coil. Far away from the coil. If it is so, then in comparison to this x, this r can be neglected because r is so small as compared to x square. So if you neglect this, then the magnetic field B is equal to, you can write mu naught I capital R square. This r you cannot neglect because here you do not have the term x square. You will not, in comparison to x only you can neglect. So in the denominator it will become twice r square is neglected. So x square 3 by 2 to cut, so it will become x cube. So that is the expression for magnetic field if x is much greater than capital R. So we have discussed this particular topic. So how to find out the magnetic field at an axial point due to a circular current loop. So keep in mind, actually we need the formula. Why I have shown you the method? Because certain cases may be given to you where you have to find out the magnetic field by using Biot-Savart's law. All the time the formulas are not going to help us. There are certain cases which you will not be able to crack by using a certain formula. Then you must know how to write Biot-Savart law for an element and then integrate it to get the total magnetic field. That is why the method should be clear. So one method I have just shown you For rest of the things, we will not go through analytically. We'll just write down the formula. Okay. So this is very, very important. So let's go for the application now. Application of Biot-Savart's law, and this time we'll just apply the formula. Okay. So let's start. So you can take a screenshot if you want. Sit down. Applications. First one. So you have to decide the magnitude of magnetic field, at the same time you have to decide the direction also. Suppose I have a circular current carrying coil, okay, and here current is going in from this side and current is coming out from this side. Going in, so current is going to flow like this and come out like this. This is the center of the circle, and I am considering R to be the radius of the circle. Okay, and I amount of current is actually flowing. So if I ask you what is the magnetic field at the center, this is already done. So what was the expression? Mu naught I divided by twice R. So you will be writing mu naught I is the current divided by twice R is the radius. Direction. So I told you, if you have a circular loop, what you need to do to get the direction of current, get the direction of magnetic field, curl your four fingers along the direction of current flow. Thumb will be giving you the direction of magnetic field. So magnetic field at the center is coming out. Coming out means how do we denote it? By dot. So give a circle, give a dot, it means magnetic field is coming out. Okay, once again, curl your four fingers along the direction of current flow. Thumb is going to give you the direction of magnetic field. Okay, done. Number 2, this you see now. Now, if it is not a complete circle, suppose you have a circular arc, and the circular arc is subtending an angle theta at the center. Let me consider R to be the radius of the circular arc. Suppose I amount of current is flowing. I amount of current is flowing through the circular arc. If someone asks you what is the magnetic field at the center, center is supposed to. Okay, so magnetic field at the center, how to get it? See now. Very simple. The formula goes like this. It is mu naught I divided by twice R. What was that? It is the magnetic field due to a complete circle. This, then multiplied by theta divided by twice pi. What is theta? The angle subtended by the R divided by twice pi. This is going to be the magnetic field at the center. Keep in mind. If it is a circular arc, here the angle subtended by the circular arc has to be known to you. Then you may be thinking how I have got it. Simple, by just unitary method. You see, if twice pi is the angle, for complete cycle, what is the angle subtended? Twice pi. If twice pi is the angle subtended, magnetic field is mu naught I divided by twice R. If 1 is the angle subtended, this divided by twice pi. If theta is the angle subtended, multiply it by theta. So that is just a unitary method. But you need to memorize the formula. Keep in mind. Okay. So this formula is very, very important. Now, how can you apply this formula to find out the magnetic field due to a semicircle, due to a quarter circle? Let us see this. Okay. See now. So here direction we have not decided. How to get the direction? Curl your four fingers along the direction of current flow. Make your thumb straight. So magnetic field is going into the plane of the pole. Into means cross. Okay. Now number 3 you see. If it is a semicircle, this is the center. R is the radius. I is the current flow. So if I ask you what is the magnetic field at the center, magnetic field at the center, the formula you know, it is mu naught I divided by twice R, theta divided by twice pi. If it is a semicircle, what is the angle subtended? It is pi. So theta you will write pi divided by twice pi. So pi cancel, 2 into 2 it is 4. So it will become mu naught I divided by 4R. I recommend this particular formula also you need to memorize. Okay, because we have to directly use these values in the numericals. So magnetic field at the center, if it is a semicircle, then it is mu naught I divided by 4R. Direction. Curl your four fingers along the direction of current flow. Magnetic field is coming out top. So that is how you need to get the direction of the magnetic field. Okay. So here it is number 4. If it is a quarter circle like this, so it is 90 degree. Okay. So I amount of current is flowing. R is the radius. Okay. then magnetic field at the center is equal to mu naught I divided by twice R. Theta means pi by 2 divided by twice pi. The formula goes like this. Theta, in place of theta, you will be writing pi by 2. Okay, so it will become what? Mu naught I divided by, see, pi by cancel. This 2 will come down. 4. 4 into 2 is 8. So it will become 8R. So direction is, curl your 4 fingers along the direction of current flow. Magnetic field is going into cross. So that is the direction of magnetic field. So if it is a 3/4 means till here. Then you will take the angle to be 3 pi by 2. You will write 3 pi by 2 like that. Like that, you will be getting the magnetic field. So that's all I have shown you. Okay. Now let me show you, if this is a straight conductor, then how to write down the direction of, how to write down the magnetic of it. See, till now number 4 I have shown you, now number 5. Take screenshot. Number 5. See. Suppose you have a straight conductor like this. I amount of current is flowing. You want the magnetic field at this point, at point P. Magnetic field at point P. So if you want to find out the magnetic field at point P, what are the things you need to see? First of all, let me take the distance of the point from the straight conductor is suppose R. Okay, suppose R. Now when I say distance, it is always the perpendicular distance, the shortest distance you want to take. Okay, so it is always the perpendicular distance. Means you will be drawing a perpendicular from point P on the straight conductor. Now, join the ends of the conductor, ends, this and this end. Join the ends of the conductor with point P. Join them. Suppose this angle is alpha, this angle is beta. Okay? So you can write down the magnetic field in terms of these two angles, or if these angles are given, suppose it is theta, it is phi. You can write down the magnetic field in terms of these angles also, both sides. So if you want to write down in terms of this angle, these two angles, then magnetic field at point P, see, BP means magnetic field at point P. Okay, is equal to, the formula goes like this: mu naught I is the current flow, divided by 4 pi R is the distance of the point from the conductor, sine alpha plus sine beta. Just keep in mind how you are taking these angles. When you are saying alpha is above the line, keep in mind, above the perpendicular line, and beta is below the perpendicular line. In some cases, if you see beta is becoming above the perpendicular line, then you have to put a minus sign. Don't forget. I will give you this case. Means if you get a case where beta is not falling below the perpendicular line, it is above the perpendicular line, then you have to take this term as negative. Keep in mind. Okay. So here the derivation I have not shown you. It can be derived as I have shown you the previous derivation by using Biot Savart's law. Direction. If I ask you the direction, now this time it is a straight conductor. In case of circular conductor, we were curling the 4 fingers to get the magnetic field. Here it is a straight conductor. Point your thumb along the direction of current. Point your thumb along the direction of current. Curl your 4 fingers, hitting the board like this, perpendicular into, so cross. Magnetic field is going into. Okay. So if you want to write down in terms of these two angles, then how will you write? Mu naught I divided by 4 pi R. Now in terms of this two angles, simply in terms of cos. How can you get it? You see, E is 90 degree. What is theta? It is 90 degree minus alpha. So you will get cosine term. So it will be cos theta plus cos phi. Simply, in these two angles, in terms of these two angles, it will be cosine term. In terms of these two angles, it will be sine term. Okay, direction is same. Okay, so either you memorize this or you memorize this, anyone, but very, very important. You need it. Now, how to apply this formula in different cases? See now, points number 6. This time you see, this is a straight conductor and the point is near to one end. Okay, suppose I amount of current is flowing. This is the point where I need the magnetic field. Distance of the point from the conductor is R. So what is the difference between these two cases? You see, here the point is not near to any one of the end, it is midway somewhere. Okay, but here the point P is near to the lower end. So you see, here what we have done, we have drawn the line perpendicular to the conductor to get the distance. Okay, and then line joining the two ends. Now in this case, this perpendicular line and the line joining the lower end is overlapping actually. If it is overlapping, what is the angle beta here? Angle beta is 0. Okay? Now, line joining the apparent and the perpendicular distance, this angle is there. Suppose it is alpha. Then magnetic field at point P is equal to mu naught I divided by 4 pi r. Okay, 4 pi r sine. Okay, let me write. Sine alpha, upper angle is there, plus sine beta. Beta is not there, so 0. Beta is not there. Because the perpendicular line and the line joining the lower end both will overlap. Overlapping means angle is not there. Okay, so it will become BP, magnetic field at point P is equal to mu naught I divided by 4 pi r. Now sine alpha is only left out. Direction is given by your forefinger along the direction of current flow. On this side it would have been going into cross, but on the other side it will be coming out because you have the point here. You are finding the magnetic field here. So on this side it will have been perpendicular to it. Why over here? কিন্তু ইফালে কি হবে উলাই আহিব তো okay. Now number 7, suppose the situation is like this. You have a straight conductor, current is I, and the point is midway, exactly midway between the two ends. That means this angle is also alpha and this angle is also alpha. Both angles are same. Both the angles are same. Then what will I write? Very simple. Here I no need to tell you BP is equal to mu naught I divided by 4 pi r and sine alpha plus sine alpha. So it will become twice sine alpha. So 2 it will be cutting it. So mu naught I divided by twice pi r and sine alpha will be left out. And direction is cross, going in. Cross. Like that. So this is how you will find out the magnetic field. Last situation. One more situation let me show you. If the situation is like this, you see, it is a straight conductor. It is a straight conductor. I amount of current is flowing, and I want the magnetic field at point P. Where is the point P? You see, the point P is falling on the line of the conductor. Point P is on the line of the conductor. Okay, so point is on the line of the conductor. Point is on the line of the conductor. Then you see how we have chosen the angle. The angles were the angle made by the perpendicular with the line joining the conductors. Now here the point itself is on the line of the conductor, so they will not make any angle. So sine alpha is also 0, sine beta is also 0, so magnetic field will become equal to 0. So BP is equal to 0. Don't forget it. If the point is falling on the line of the conductor itself, then there will be no magnetic field at that point. Created by whom? Created by the conductor. Conductor will not produce any magnetic field on a point which is on its own line. Don't forget. Okay. So one more situation has come to my mind. So that is the last one. So suppose 9. Suppose situation is this. I amount of current is flowing. Okay. And the point is here, below the conductor. Here it was in between, okay, in between the two ends. So it is below, okay. So then, to get the perpendicular distance, what we need to do first of all, we need to extend it, otherwise we will not get the perpendicular distance. So perpendicular distance is this, R. Okay, I amount of current. You have the conductor from here to here. This is just we are producing it to get the perpendicular distance. Fine. So we need the angles now. Okay, so to see the angles, we have to draw lines joining the ends with the point. So it is the line joining the upper end. It is the line joining the upper end. Okay, and it is the line joining the lower end. We have called the angle made by the perpendicular with the line joining the upper end to be alpha. So you see, this is the perpendicular line. Okay, so angle between the perpendicular line and the line joining the upper end, alpha. Perpendicular line and line joining the lower end, beta. Okay, now magnetic field at point P is equal to mu naught I divided by 4 pi r sine alpha is fine because alpha should be above the line joining. Alpha should be above the perpendicular line. Yes, above the perpendicular. Alpha is fine, but beta, you see, the angle beta is above the perpendicular line. But by definition, it should be below. So this term has to be taken as negative. That's what I told you. This term has to be taken as negative because this angle is above the perpendicular line. Okay. So about the direction, Point your thumb along the direction of current flow. So your four fingers are hitting the plane of the board perpendicularly to cross. Magnetic field is cross. So these are the cases how we can apply this particular formula to get the direction of magnetic field due to a straight conductor. You got to know about magnetism. You got to know how to get the direction of magnetic fields. So you can take a screenshot. Thank you. So I'll meet you in the next class with another topic. Bye bye.